All right, so let's take a look at something similar to what we covered in the previous video where we were looking at the perpendicular bisectors and the angle bisectors in a triangle and how they all intersected at a common point or they were concurrent. In this video, we're going to take a look at two other kind of important segments within triangles, medians and altitudes. So we have not defined these terms, median and altitude, so let's go ahead and do that first. A median of a triangle is a segment that has endpoints that are at a vertex of a triangle and the midpoint of the opposite side of that vertex. Right? So we're looking at a segment that starts at a vertex and goes across to the midpoint of the opposite side. So if we look in this picture, we have triangle ABC. Look at segment BD here. Segment BD is going from a vertex, or one of the corners of the triangle, and it's going across to point D. And point D is the midpoint of segment AC. I can see that it's divided segment AC into two congruent parts. So D is a midpoint, right? D is the midpoint of segment AC. So segment BD would fit this definition of what a median is. It's going from a corner across to the midpoint of the opposite side. An altitude of a triangle, something a little bit different. It is a perpendicular segment from a vertex of a triangle to the line that contains the opposite side, which is a little bit of a weird way of phrasing it, and you'll see why we have to phrase it this way in a minute. But if you look at segment CE in this picture, we can see that it is going from one of the corners of triangle ABC. It's starting at C, which is a vertex of triangle ABC, and it is perpendicular to segment AB. Technically, it's perpendicular to the line that contains segment AB, right? If we were to turn segment AB more into a line here, segment CD is perpendicular to that line. So it fits the definition of an altitude, going from a vertex across to either the opposite side or like a line that it contains the opposite side and is perpendicular to it. Now, the reason why we have to phrase it this way, instead of saying it's perpendicular to the opposite side, that we have to say it is perpendicular to the line containing the opposite side. The reason is because of obtuse triangles. In an obtuse triangle, two of the altitudes will be outside the triangle. And I'll try and sketch an example of this for you to kind of see why this happens. So let me just sketch an obtuse triangle. So let's just look at an obtuse triangle that maybe looks like this. If I was trying to draw, let's call the sides, the corners A, B, and C. If I was trying to draw an altitude from point B, right? If I was trying to go from point B and draw an altitude, because this is an obtuse angle here, there's no place that I could get to on segment AC itself to make a perpendicular segment, right? Any place I go on segment AC is not going to be perpendicular to it. So what I have to do is I have to kind of temporarily imagine extending segment AC into a line like this, and then my altitude gets dropped straight down like that to that line. And then the same thing would happen if I was trying to do an altitude from point A. I can't go to anywhere on segment BC to make a right angle. Instead, I have to kind of temporarily imagine extending segment BC into more of a line, and then I would come across like this to make my altitude. All right. So that is that's why we have to say to the line containing the opposite side, because occasionally we have to take one side of that triangle and extend it into a line to drop the altitude down to it. So in an obtuse triangle, you can see two of those altitudes are outside the triangle. The third one would not be. The third, if I was drawing the altitude from C, it would just come across here, and you can see that altitude is still within like the interior parts of triangle ABC, but these two are outside. So that's what altitudes and medians are. Now let's look at a couple ideas about them, because you might have predicted, just like perpendicular bisectors and angle bisectors, they are going to be concurrent. If I look at a triangle and I draw all the medians of a triangle, I could draw one from each vertex, right? I got segment AD, which is going from A across to the opposite side's midpoint. I got segment BE going from this corner to the opposite side's midpoint. And I got segment CF going from this corner to the opposite side's midpoint. They are all medians, right? So they are all medians. And you'll notice that they are all intersecting at point G. So that means they are concurrent. They are concurrent, and what's special about that point, first of all, it's called the centroid of the triangle. It has a name, just like the concurrency of the perpendicular bisectors was called the circumcenter, and the angle bisectors is called the incenter. The concurrent point for the medians is called the centroid of the triangle. And the centroid is, what's special about it mathematically is it is 2/3 of the way from the vertex to the opposite side. So what does that mean in our picture? How do we interpret what this is telling us about if I look at this picture? Well, if G is our centroid, then the distance from C to G, is 2/3 of the distance from C to F. And we could say that same thing about from A to G. A to G is 2/3 of A to D. And we could say the same thing about B to G. B to G is 2/3 the distance from B to E. I sometimes think about this maybe a little bit differently. I look at the centroid and I look at each median and I realize that that centroid has divided each median into two parts, but they're not equal sized parts. There's a smaller part and a bigger part, right? GF, if I look at segment CF, the median CF, it's got point G right here, the centroid, and point G is breaking it into a small part, segment GF, and a larger part, segment CG. That small part down here is always half as big as the large part. And it comes from this, right? If this is 2/3, then this would be 1/3. So if that's 2/3, this is 1/3. And 2/3 is twice as big as 1/3. Or we could say 1/3 is half the size of 2/3, right? If you're thinking about a pizza and I get 2/3 of the pizza and you only get 1/3 of the pizza, well, I got twice as much as you did, right? You got half as much as I did. So that's the way I look at that centroid. I look at it as taking each of these medians and breaking it up into a smaller part. Right? Let's say we got the purple part, which is the smaller part. So each of these medians has this smaller part, and then it has a larger part. I'll use blue for the larger part. All right, we got segment BG, which is the large part of median BE, segment CG, which is the big part of segment CF, and segment AG, which is the big part of segment AD. And each time, those large parts are twice as big as the small part. So I'm going to write that down here. I'm going to say that AE, in this picture here, I'll do it over here, AG would be equal to 2 times DG. And I would say that BG is equal to 2 times EG. And I would say that CG, I'm sorry, that says BC, it's supposed to be BG. And I would say that CG is equal to 2 times GF, or FG. And that's another way to think of the same idea of what this is saying. Some people don't like the fraction part here, right? They don't like the fact that we got to take some number and multiply it by 2/3. It's a little bit harder to do. So instead, I would maybe say, think about the big part of each median being twice as big as the small part. Fun fact about the centroid is the center of mass for any triangle. And so what does that mean? That means the center of mass is kind of like the balancing point for any object. You can always balance an object at its center of mass. So if you had a physical triangle, like cut out of metal or wood or cardboard or something like that, and you found where that centroid is, theoretically you could balance that piece of cardboard or metal or wood. You could balance it right on that centroid point because it's the center of mass. And that's just kind of an interesting fun fact about centroids. Last thing we need to talk about is something called is theorem 5-8, which is the concurrency of the altitudes. So if you look at the three altitudes of any triangle, they will be concurrent. So in this picture, it's a little bit hard to see, but we have triangle KML, and we have three altitudes drawn. We have, let's see here. So if we look at triangle KML, we have segment MP, which is an altitude. I'll highlight it in purple. We have segment KQ or line KQ, and then we have segment or line LN, right? And you can see they're all intersecting right here at point X. So point X is the point of concurrency for the altitudes of a triangle, and it is called the orthocenter. And that's about all you need to know about it. The three altitudes are going to intersect at a point called the orthocenter. I guess there's one other thing. Got a question here that says, where will the orthocenter for an obtuse triangle be? Well, if it's an obtuse triangle, we already talked about how two of those altitudes will be outside the triangle, and that means that our orthocenter will be outside the triangle. An acute triangle is kind of like what we see here. That orthocenter is going to be inside the triangle. But then let's think about for a right triangle. Let's think about what happens. Let's sketch out a right triangle and look at where the altitudes might be. All right. So here's my right triangle. If I draw the altitude from this corner, actually let's start with here. The altitude from the vertex where the right angle is, it's going to just kind of come across here, and it'll be like that, right? So we can extend it into a line if we want. That would be the altitude. But then if I look at the altitude from either of these corners, it's got to go across to the opposite side or the line containing the opposite side and make a 90-degree angle. Well, I already have a segment that's doing that, right? It's this leg right here. So this right here would actually be the altitude coming from, let's label these, let's call this point A, let's call this point B, and let's call this point C. The altitude that's going from point B is going to be actually this side of that right triangle. And then the same thing's going to happen if I'm drawing the altitude from point A. So that point of concurrency ends up being point C. So for a right triangle, the orthocenter will be, it'll be the vertex of the right angle. The vertex of the right angle will actually end up being the orthocenter for any right triangle. So obtuse triangles have their orthocenter outside the triangle. And again, if you look up, let me just kind of scroll back up here to my sketch of that obtuse triangle. If I was to extend each of these into a line, these are my altitudes, remember. If I were to extend each of those into that line, we can see that orthocenter happening right there, well outside this triangle. And then for an acute triangle, it's kind of like maybe the normal situation where the orthocenter happens to be inside the triangle. Right triangles have it at the vertex of the right angle.